2 days, 40 days. So we start again from the lecture 5th. Now the second part of the application of nanomaterials. So first subject is the inelastic mean-free path. And after the coffee break, we discussed the semiconductor and the superconductor thin films. Just to remind the previous talk, so this is the coordination number. The FCCs, the atoms are surrounding to the 12 atomic, and as a particle size decrease, the coordination numbers, the average number of 12 the surrounding atoms decrease. This is because surface effect, the surface areas increasing, so the average nearest neighbor atomic also decrease. Now this is a special information from the exhaust. But now we pay attention to the determining the coordination number for a small metallic particle, because the inelastic mean-free path change to the smaller particles. This head cover is I show you the gains, mean-free path, the universal curve like this. The energy of photoelectrons, the long mean-free path presents to the multiple scattering in the Zarnes regions. In exhaust regions, the mean-free path show the simple functions depending on the electron energies. Now this is the result of some example of the palladium nanoparticles. The particle size was determined by small angled X-ray scatterings. And bond length and coordination number is determined from the exhaust. So diameter, as diameter decrease, so the bond length also decrease. So the metallic between the interatomic bond strength is increasing. And coordination number is also decreasing. So this peak position means the peak of the sacs. So it's corresponding to the particle diameters. So estimated value of the simple calculation, the model calculation from like that. So that is this curve. But unfortunately, the exhaust result is smaller than the coordination number for the expected value from these models. In the case of the bond length, the model and the exhaust result coincide, almost same, is satisfactory. Now we consider the effect of intrinsic loss or extrinsic loss or the mean-free path. In other words, is the lifetime of the photoelectrons. So in the exhaust equations, the mean-free path effect are incorporated to like such functions. Of course, the no infinite mean-free path show the no reduction factors is a unit. But some comparative to the about 10 to several 10 angstrom is usual for the exhaust regions. So this is effective to for the reduction factors. Historically, the Penn's algorithm or TPP2M method, I don't know in detail this method, but it's original calculation to the photoelectrons are available. So we're using generally using the IXAS calculations, so FE, FF, and it's incorporated to the antenna, Artemis. The mean free paths are all automatically calculated. So from this algorithm. But this algorithm is based on the bulk state or infinity periodicity of atoms. On the other hand, for smaller particles, the Plasmon excitation are effective. So in this part, we discussed how to take into account for the Plasmon excitation to the electron mean free path. Our model is very simple. This is originally developed by the Japanese scientist Fujimoto Komaki and American transfer to the IXAS result, IXAS treatment, Tau and Montano. The electron gas is models, and photoelectrons go through to this gas and excited to the Plasmon mode of this electron gas. So in this case, the A is the particle size. This is also in the nanoparticle matter. Nanoparticle size and electrons filled in these particles, like a gas. Omega or nu is the Plasmon's frequencies, excitation frequencies. K is the momentum. From these models, the Plasmon excitation total transition probability from the Plasmon excitation here. There are three terms, and the first term is expressed to the bulk models. So this is a bulk excitations. The omega p is the Plasmon frequency for bulk. And the second term and the third term is from the surface Plasmon excitation. The plane wave expansions using the Bessel, such kind of Bessel functions. The L is the quantum number. So there is also the Plasmon frequency for bulk, but this is the effect of the surface nanoparticle, circles particles. Second one is also particles, and the function is diameter is there. Of course, this surface effect depends on the inverse square of radius. So radius is small, becomes small. This effect becomes large. Now we calculated for example potassium to sodium. So these simple metals. These simple metals has no 3D electrons. It's possible to models of circle electrons, our simple electron gas. And the relaxation time of Plasmon is, for example, calculated by these orders for aluminum. And we check these parameters, so several nanoparticles. It's not so sensitive to mean free path. plasma excitation from the bulk is a wide energy range from the potassium 4.4 to the beryllium about 18 electron volt. The result of here, this is a plasmon excitation spectrum for the electron volt for probabilities. For example, the large particles, there it's only bulk plasmon peak prominent with small surface excitations. But the smaller particles, 30, 20 angstrom radius, so the surface plasmon becomes prominent. And these fine structure come from the this Bessel expansion by the Bessel functions. The same result is obtained for another calcium atoms. Now we summarize. We move on the calculation of inelastic mean free path of photoelectrons from this probability density, probability function by surface plasmons. So we integrated of this excitation curve, excitation areas, and integralize the all areas of the electron gas. For the example of the magnesium and the calcium is like that. The energy is the photoelectron energies, and this is the mean free path. And the value is around several 10 angstrom. In the case of Ixas, the up to 1,000 electron volt is limited. So these values are limited to the 30 angstrom. Usually, sometimes we approximated of this curve for the linear lines. Of course, in the FEFF or Artemis, this bulk curve is calculated. For calculation, calcium, the same curve is obtained for the smaller particles and the larger particles. So this is a summarize of these all our model substance from the different plasmon excitations. This is a function of particle size on a mean free path. The effect of the particle size, the effect of plasmon frequencies is here. So smaller plasmon frequencies show the large mean free path. It is very natural. So energy is small, so the integration is very small, and inverse relations mean free path still long. But the large excitations, the energy move to the plasmon excitation, so the mean free path becomes small. This is natural from the basic physical explanations. And the particle size. For about the 500 angstrom, there is a constant. So there is no particle dependence of the particle size. But smaller than the several hundred angstroms, the mean free path becomes very short. And about 100 or several 10 angstroms, the degrees is very steep enhancement. Now, we calculated for the silver nanoparticles. Check our result in the previous talk. So this is a calculation result of the transition probabilities for plasmons. For energy is plasmon frequencies. The stronger peak, the higher peak is from the bulk plasmon for silvers, and the lower energies from the surface plasmons. In this case, the energy is very large, and in the case of the silvers, the electrons is filled. Much electrons is filled in the atoms. So in the electron gas. So this is not clear. So the Bessel expansions, but this is a 1, 2, 3, 4, 5 is a higher order Bessel functions. For large particles, about 100 angstrom, there is no surface excitations, only bulk excitations. As the particle size decreases, so that surface effect becomes larger and bulk effect becomes smaller. Oh. We check the exact result of the exact, so we calculated to this mean free path. So the exact, in the exact equations, the mean free path is comparated to the exponential functions. So we assume that this mean free path functions, depending k dependence, is the linear relations. In this simple relations is taken into account by the Taylor and Rees. The eta is expressed as the imaginary part of the self-energy of electrons. This energy is expressed as the extrinsic loss. So from our these calculations, we check transfer to the k-dependence electron moment dependence of the mean free path from the large energy, large particles and smaller particles. And we obtained this linear coefficient eta. The eta plotted to the particle size here. So large particle size, about 100 angstrom, it's also saturated. Is from the FFF. This is a bulk calculation from the bulk. And the smaller particles, this imaginary part of the self-energy increasing. It has a relation to the plasma excitation. The effect of the plasma excitation increasing in the smaller particles. So we use this eta values to the fitting of the curve exact result. So obtain the correction data of the nanoparticles. So green one is from the direct curve fitting using the single atoms, single eta atoms from the bulk. using the FFF or Artemis. And, now we correct by the incorporation to the take into account to the nanoparticle effect via plasma excitations. Leave it higher. Correction data is higher, not so small. So now we pay attention to the EXAS analysis for the nanoparticles. The EXAS result is here to the smaller values, present to the smaller values than the real particles, real coordination number for the smaller metal particles. This model, finally, I summarize of these sections. This model is from the electron gas model. So maybe this is applicable to the metal particles, and plasmon loss energy appears. But in the case of the semiconductor or insulators, we don't have any ideas in the present in that case. So we pay attention to some coordination, check the coordination number obtained from the EXAS, usual EXAS method for the very smaller particles. Okay, just 30 minutes, but now next topic is different. Too fast? No coffee? No coffee? No? 11, coffee 11. Okay, I continue to this talk. Just a short break. This is a different topic. As you know, this is a new, the end of the 20th centuries, Japanese scientists discovered of such kind of blue LEDs. In blue LEDs change the society for the Pacific signal or computer displays or something. So blue LED is very useful for the very short wavelengths and much information in the storage device. Not only, but that also it makes the white LED colors. White LED is very useful for some very bright light. So here is the review from the Shuji Nakamura. He discovered the blue LEDs, but still the green one is not available. The blue one is here, red one is here, but this shows the green gap. It is difficult to the green LEDs. Usually we use this such laser pointers. The green ones, that is not direct greens. That is used to the second excitation process for the red one. So the first blue laser is excited in such kind of quantum wave. And the second step is using another mirror indice. For example, this is the C brains. First, they discovered the blue LEDs, but the C-axis sample, C-plane sample is very high cost. It's difficult to clean samples. The second step is the M-plane crystallizations. In this case, there is no distortion of these directions. And its cost is already high. So another future trial is this type of brains. This cost is quite low. So I talked today to the first with the normal C-plane samples, and then how to analyzing of these M-plane species. This is the example of the emission energies as a function of indium component. Usual indium gallium nitride shows the red emissions or amber emissions for higher concentration of indium. And about 0.2 component show the green excitation, green emissions, and lastly the very smaller portion of indium, so it emits to the blue colors. So our sample is very thin in extreme conditions. Substrate here and buffer layer is here, so active layer for the including the indium is just 3 nanometers like that, and the cap layers here. So these thin layer indium active layers is epitaxially produced. So we use the polarization exhaust techniques in planes and out of planes. And indium has very high energies. So this spectrum is from the spring 8 for using the undulator lines device. And it takes several days, even using the singleton radiations, but it's very long time to obtain these quality of data, such a quality of data. The Fourier transform of these samples. The first one is, of course, the indium nitride. The second one includes to the indium gallium and indium. Indium atoms are replaced by the gallium positions. So the zinc blende structure, typical zinc blende structure. The result is here. For we measure these 3 concentrations, three concentrations. X equals 0.14 is blue color LEDs, and this is green color LEDs. Final one is amber or red. The 3 type of the colors shows these results. Of course, the first peak is the same as 3 type of colors, about 2.1 angstrom. After the curve fittings, For the second one, we concentrated to the discussion for the indium gallium and indium indium. So second nearest neighbor peak. For in plane, there's a 3.22 angstrom, and outer planes is a longer one. Indium indium is also the longer than outer plane, longer out for outer plane than in planes. This means the for very small thin layers, gallium nitride substrate makes the indium gallium nitride structure is compressed in the AB planes. This is the first result from this X-axis result. And secondaries, we check the coordination number, effective coordination number of indium-indium. For smaller indium atoms, both, all three indium atoms, the indium concentration is larger for out of planes. Out of planes is vertical directions than in planes, in AB planes. So that means schematically, that means schematically is for the top views in the AB planes, indium atoms are distributed randomly. But from the horizontal ways, the indium coordination is larger than the in planes, so it means the indium galliums gathers in the C-axis. We check the more accurately for three. We measure the three samples of here and divide it is a normalized indium concentrations divided by this one. So for y over x show 1 unit is a completely randomly distributions, and higher than unit, it gathers or some fluctuation. There is some fluctuations for the blue one is the AB planes, and black one is the AB planes are black one. So AB planes in the planes are randomly distributed. So the location, dislocation or fluctuation is appear in the lower concentration of and C-axis. This behavior is quite similar to the this quantum efficiency depending on the indium concentrations or emission wavelengths. These marking three samples are same as our measurement of X-axis. The red colors emissions is also almost very small quantum efficiencies. This sample is here. So randomly distributions make related to the small quantum efficiency. But another two has large quantum efficiencies. It shows composition fluctuations in the out of the planes. Now we move on the how to analyzing to the M plane. Indium gallium nitride films. In the case of the M planes, the sample preparation is very complicated. First, we made a gallium nitride substrate and cut. Usually, atoms are produced in the C-axis like that. And after that, we cut the M planes very sharply. And the next steps, these indium gallium nitrides, these buffer and samples are produced on the M planes. This advantage of what is the disadvantage of these C-plane samples? Atomic compression is appear in the AB plane, so the atoms move to the distorted to the C-axis. So there is a electric field mismatch or moving. So this effect reduced to the quantum efficiencies for the model of the quantum mechanics. So the M plane is C-axis is here, and this is M plane, M axis. No electric field distortions on the these M planes. Yes, we call the electrostatic field axis, and induced to the quantum confinement Stark effect. So this also became the degrees induced to the degrees of the oscillation strength, electron fold pair. So the M plane sample has a merit for the inhibit or discuss to the degrees of the oscillation strength. Now our sample dimension is here, and our polarization of X-ray is horizontal ways. First, we measure to the polarization is parallel to the C-axis. This means the C horizontal. Second step, we measure the A3 axis parallel to the electric field. Thirdly, last one means the our electric field is the vertical to M planes. Right. First, electric vector is here, these directions. Secondly is these directions. Last one is these directions. I show you the result first. This is the exact functions of X-ray absorption function of these three M plane samples. The comparison to this is the C plane axis, C plane samples. In the case of the C planes, the same effect of the A direction and B directions. So this is the A3 axis. Only C axis are different. In the case of here, the C axis is completely different of the A3 axis. In case of the M planes, a small change appear in also C axis. Of course, C axis is different symmetries than A3 and A1. So the A3 axis and M plane, vertical to M plane axis, quite similar, but slightly different. X-axis function is also the C-axis is defined, and the C-axis also defined from here. And X-axis Fourier transform is like that. Our sophisticated technique using the polarization of the synchrotron radiations. No, effective coordination is expressed as a cosine function of incident angles. For example, I showed you already in the previous lecture. Electric vector is parallel to the AB planes, so only these informations are obtained. In the case of the glancing angle incidentation, so the X-axis is relation it comes from to this perpendicular of the surface information. Now, first, we measure the electric vector is parallel to the C-axis. So we can categorize three kinds of indium atoms, indium or gallium atoms. This is the central indium atoms, and these first atoms are around on the C-axis, and the second one and the third one. Second and the third atoms are in the AB planes. So in this case, the X-axis obtains the information of only first labeled atoms. There is no contribution from the third and second atoms because these relations, cosine functions. So first we determine of the structure parameters for these one labeled atoms, labeled one atoms. Second step, our electric vector is parallel to A3s. In this case, the X-axis detect only first labeled and second labeled. Three labeled atoms are on the 1, 1, 2, minus 0 axis. So, and we, for the structure of the one labeled atoms are already determined for the first step, previous step. We use these parameters. So this step we can we can determine to the structure parameters of these second labeled atoms. Finally, we measure the electric vector is parallel to the 1, 1, 2, minus zeros here. So in this case, all atomic information is included in X-axis spectrum, but first and second labeled atoms are already determined in the previous steps. So in this case, we can detect to the only number 3 labeled atoms. Oh, this 3 steps method appear the atomic structures for independently. For C-axis, M-axis, A-axis. This is simple. This is indium nitrogen, so that this is simple. The 1, 2, 3 on only 3 areas for about 0.10 over 0.9 or like that. Coordination number is also 4. This is very natural, within error range. But it is interesting to the 1 labeled atoms, 2 labels, 3 labels, indium gallium or indium. So first step we determined of this first 1 atoms, and we also focused on the coordination number of indium against. This is a very interesting parameter of this system, 0.9. And the number 2 is here, is 3.28. And the number 3 is 3.25. In the result of the C-plane samples, number first one is the C from C-axis. It's the longest one, elongates, compressed in the AB planes and elongate in the C planes. But in this case, the M planes, the C-axis are free from the any stress. So the number 1 atoms is not so long. But it is interesting to the number 2 atoms. This is the M plane is here, so number 2 atoms are located in the perpendicular of surface. Yeah. Surface. Of course, number 2. Number 2 atom is here, and number 1 is in the surface, and number 3 is also in the surface. Number 2, only number 2 atoms are perpendicular of the surface, M plane surface, so it's free from the compress or free from relaxed, free from the complex. It's a relaxed, so that it's a very long, slightly long bond length. And here is the coordination number of indium. So this sample is very small portion of indium. The average concentration is 0.05. So this coordination number is slightly larger than of these components. The percentage is 6%. The whole coordination number, it should be the 12. I don't know. Check the 6. 12 times 0.6 is smaller than all of this. So in this case, also the indium atoms localization is appear in this sample. So that is the result of the analysis for such kind of interesting M-plane structure of zinc brain structures, semiconducting systems. So we can remind how difference between the C-plane samples or M-plane samples. Okay, next topic is another superconducting films. So if you have questions or comment, please send me, and after that, we go to the tea break. Do you know the usage of the Blu-ray LED or Blu-ray laser? Of course, the Blu-rays has a short wavelength, very natural to the storage area is very small, so very condensed informations are stored inside the disk. Another usage is red one is already discovered, and red ones, blue ones, green ones, it makes 3 component of colors. So it makes white colors, white colors LED is available. Unfortunately, this is not LEDs, but LED lamp is too bright, so it's not so good for my eyes. Any question or comment? Question or discussion? No? Oh. What? What? Component of the indium became the control to the gap energies. For in the case of the a small portion of indium atoms, became the gap is very large. So the emitting color is show the blue shift. The quantum levels becomes, indium gallium nitride is essentially the active layers. Only that layers produce to the emission the colors, but all of the indium atoms are controlled to the gap length, energy gap. So much indium atoms energy gap is very small, and smaller indium combination becomes gap is large, and the color is changed to the blue. Yes, external quantum efficiency. That is another method. We don't know in detail, but that's the result our colleague used for the production of these samples. Measure. Material? I'm talking about reason of the change of quantum efficiency. I'm sorry, I don't know that in detail, quantum efficiency. Okay, there are no questions. No coffee break.
When you came back,
10 or 11.
in the night,
Long drive, but
you could see the dragon.
yes, but unfortunately, didn't
See the tiger.
Oh,
Two tigers went there, so how the tiger can come out? See, you have one more lecture.
yes. After this.
How many lectures do you have?
Yes, one lecture this afternoon. And,
No. Tell me the
no. This after course today. One lecture.
Okay.
And last week, tomorrow, I have.
No tomorrow.
Just no, this is.
Oh, you finish everything today?
Just.
Just one. You have lectures.
So, tomorrow. This is tomorrow.
No, tomorrow. Today.
Today is tomorrow.
Okay.
Lecture 5. Lecture 5. Yes, lecture 5. Latter half of lecture 5. Tomorrow morning. After PT.
And then you have lecture 6. One more lecture.
One more lecture.
Do you have anything for the tutorial?
Yes, the short lecture.
Tomorrow, I will take the class. I'll show you something about the signal contributions. Then we will have the exam. Then we will go for the rest of the students will go for the lab class. Half of them will do the same tutorial which you are doing today. Lecture 5. No, you have 7.